easily consumable, getting fancy with it a little bit. Full concentration. Yeah, so this is meant to be like an entry point or entryway into Vex for artists. So we'll just be making this animation. I was posting it to Twitter and that kind of stuff earlier today. Yeah, so all of this stuff is just created using a single Wrangle node. So it's 100% procedural, no simulation or no solvers, cache, or anything like that. It's just using this point generate. You could kind of parameterize this and add as many bouncing balls as you want or whatever like that. So everything's getting calculated on the fly in this one Wrangle. And it's just going to be a kind of introduction to Vex, like setting attributes, doing basic shaping functions, trigonometry. It's not meant to be super scary, just kind of getting started. So we have the Houdini file share system set up. If you do exclamation mark hip, that will give you my file. So if we get started here, just do this geometry. That explains how to get yourself set up with the shelf tool and everything. So I'll just do this as pure Vex week 1 with my name. Do a line just to get started, and then a Wrangle. So go over this a little bit. Just set something here with the X position from the Y position. Then you have just like an angled line. So I'll just save this file. Click the share button on my end. So this will be like the starting scene. I'll continue to update it. If you have the shelf tool installed, you can click it on your end with just like hip sync, and then that would merge another or my latest kind of working file into your file. Or you can just download the files by clicking on that link in the chat, whatever you prefer. So the idea here with Wrangles, just getting started here with this syntax, when you're doing an equal sign like this, you're setting whatever's on the left side of it to this, whatever it evaluates to. So if I set the X component of position to 1, all of the points get set to the number 1 for X. So just look at this geometry spreadsheet. It's a really good way to figure out, like, check what's going on under the hood with your results, kind of like debugging. So if we just do the position equals 1, this sets all of the components equal to 1. And another way to kind of visualize this, if you're used to using attribute VOPs or any programming language that's like a visual programming language, oh my God, Blake, thank you for the raid. Let's go. We're just getting started here with getting into some visual programming type stuff. We're creating this little kind of programming animation using Vex within Houdini. So if you're just getting started with Houdini or interested in programming, you recommend it's a good introduction, a good starting point. If you're not following Blake Catherine, anyone in here already, I recommend you do, highly recommended. She's a featured Redshift artist recently with a really good still life that she was working on in her stream. So yeah, we're building this and we're just getting started here. So typing out this code at p equals 1 is the same idea if you're doing visual programming or any kind of like shader. A lot of shader editors use this interface. And it's the same idea as just wiring up a node and connecting it. So this is doing the exact same thing as this over here, setting P, the position, to 1, and then you look over here and all of these numbers are getting adjusted or changed to 1. Require medium knowledge of Vex for this. This is meant to be an introductory, so like even with no Vex knowledge, if you've used Houdini a good amount, it's a good place to start for you. That's kind of the intended audience for this course or this demo, but different skill sets you could still learn and pick up some things, I think. So this is just setting P, the position, equal to 1, or overwriting it. That's what this equal sign means here. It's if you're used to algebra or stuff like that, it's a similar idea of like y equals x for graphing and kind of stuff like that. Is it possible to increase the size of the UI so the Vex code is bigger? Diener Daddy, thank you for the 2 months. Let's go. I could try to, I don't know how much it's going to mess things up. I could try to adjust my UI scale. It can kind of screw with things on my end a little bit because I think it throws off like the cursor position with Vex, but we'll give it a try with the editor, but we'll give it a try. We're in it. We're just getting into it, but yeah. So this is the end result. Estimating like an hour or so, and we'll get here. Yeah, so it's just thinking about basic, kind of like your graphing calculator and stuff like that. All right, so we have a little bit bigger of a code editor. You just go to the edit, preferences, general user interface. You can change your Houdini UI scale. Get back to where we were. So yeah, this is just setting P equals is setting all of the components of that attribute to 1. If you do at P equals an original component, like Y, then that sets all of the parts of the line to the height of the original line. So starting here, we just had a line that was going straight up from 0 to 1, and then everything is getting that same attributes copied over. If we go back over here, I'm not going to keep doing this a ton, but just for people used to visual programming, it's the same idea as kind of doing this. You're just taking the one component, the Y, or the second number from the spreadsheet and putting it into the P position. So if you do X equals the Y, you kind of have like a graphing calculator line. If you're used to, I don't know if you're back in the geometry math class days or whatever, if you were typing in things, you probably have this equation burned into your skull somewhere. This is like y equals mx plus b. So that was like a slope line intercept equation or whatever. If you do it here, you can kind of replicate it. So what we're doing is 2 times y plus 0.5. So what that is doing is changing the slope here to 2. It's kind of like a multiplication. And then adjusting the intercept to 0.5. So instead of hitting it at 0, it's going over to 0.5. That was when it started to get crazy. I guess I never got too much further than that. So in college, I was doing a art kind of major. There was no math requirement, so I stopped taking math in college. My math degree quickly capped off at that point. So I'll just do Alt drag to keep making more of these. So this is just the general graphing equation type stuff. If you do the sine function, then you're starting to get a sine wave. The way that this sine curve works, or the sine function, is that each, the argument for it is expecting kind of like pi. So if you multiply this by like whatever is close to pi, 3.141, I think I need some more points, just to have some more resolution or divisions or whatever for this line. Then you're starting to see the sine curve. So this is just half of a wave with a peak. Peter Bowles, thank you for the tier 1. If you multiply that again by 2, then you have like a full sine function. Use $pi. Yeah, that's completely valid as well. This is just an introductory course. I didn't want to get too much into extra things that are unnecessary for right now. Could do multiply it by 4, and you see it just keeps going on and on and on. So yeah, that's kind of like a graphing, thinking like your graphing calculator or making these equations is a really useful way to get started with Vex and just think about it as you're visually making these shaping functions or animation curves. So you could start to think about kind of how this is useful. I'm just gonna switch this over a little bit. We'll just go back to the empty expression. All right. So we'll take the x component, this horizontal direction or axis, and set that equal to the height. So we do this, and then we just get a diagonal curve, a constant slope or a linear kind of equation of just taking the height and then moving in the x direction the same amount as the height. So hopefully this is a good entryway into getting started with things. Then I'll just take the height and modify it. So again, you start to see this bending. This is the start of a sine curve. And the next thing we'll do is go back and multiply this by our kind of approximation of pi. And you can see we get one peak, 1/2 of a wave. This kind of looks like the bouncing of a ball. So this is going to be the start, or the way we're going to end up with this animation over here, is using this sine function to represent like a bouncing ball. If we keep going with this, you want your ball to keep bouncing. You start to see it goes under the axis. So if you're envisioning like an animation curve, you're used to working that way. If I do like shift, click here, you have an animation editor with all the 3D softwares. You're probably used to setting, overriding your parameters or setting positions, keyframing them, and maybe creating curves like this if you're doing like springs, a bird flapping its wings, or things like that. It's pretty similar to creating those keyframes by hand, but here we're generating them using mathematical functions. So yeah, I could go through the first 2 lines again. One useful thing with Vex is if you just do 2 slashes, is a way to create a comment. You can use it to disable code from executing, or you can also use it to make notes for yourself. So with this first line, I'm just going to type English here. This is just like saying the compiler will ignore it, or the computer disregards anything with the 2 slashes in front of it. So we're setting the X or the horizontal position equal to the height, or the Y position. So Vex, these programs run, the code runs simultaneously over every point that you feed into it. And when we take the Y coordinate and set X equal to the Y coordinate, that's basically just copying everything in this column over to the X column, or all of the height gets set equal to the all of the horizontal motion is set equal to the vertical motion, if that makes sense. So that's the starting point. That's all that's happening. Another way to think about it. Actually, I don't want to do that right now. We'll just keep going with this. Then the next thing we're doing is setting the height, say, to the result of a sine function. All right. So hopefully this is making sense to most people so far. Can keep kind of circling back if it's not making a lot of sense, but I think the best way to kind of go is to just keep kind of plugging along, and hopefully more and more things make sense to you. A lot of this stuff, at least to me, the way that I learned it was just through kind of repetition, looking at visual results. If you look at the Bees and Bombs Tumblr or Twitter, I think he does most of his stuff on Twitter now, trying to eventually get to the point where you can recreate that. Breaking things down into little steps is a good way to do it. All right, so we have a sine function, and with these multiplications here, we're basically just making it repeat 4 times, or I'm sorry, 2 times. We could just say, you do it once, this is 2 pi, and it gets kind of 1 loop. And then the more you multiply that, the more loops or repetitions you get of it. It's kind of like a oscillator, just going up and down and up and down and repeating over and over again. So the next thing we can do is we want to bounce the ball. Means you are overriding the initial line. Yeah, overriding the initial line, setting the height to a modification of itself, if that makes sense. So even if we don't do anything in the X direction, what this is doing is just keep kind of repeating or cycling the height over and over again. And then as this X number grows out, is just expanding things in the X direction. So we're taking the original height and running the sine function over it to modify the result of itself, if that makes sense. Then the next step we're going to do is reflect or bounce the ball. Kind of just referring to this curve as like the trajectory of a ball. So reflect the curve across the y-axis. The way to do this, there's already a built-in function for it. Again, we'll just modify the current value of the height. So we'll say at p equals absolute value of at p dot y. So I need some more resolution of my line, or I just need to do less cycles of the sine wave. So we have one bounce right here, boom, and then it lands again. So without this just goes negative. This is absolute value will just give you the positive result. It's just reflecting or mirroring something across the origin. Or another way you can think of it is kind of like folding something, like if you're folding a piece of paper. So if I just start with a grid here, for example, I'm just going to rotate it 45 degrees. And then I'll do a wrangle. And we're going to look at the x component. This x direction. If you look at the bottom left of my viewport, you can see which axis is the x axis. If I take the x position and make it the absolute value of the x position, it's a little hard to see, but we've basically folded that kind of like a piece of paper. You folded it in half. If I make another transform node above everything and go left and right with it, you can see as it's, instead of returning negative values, we're folding everything over itself. And then if you keep going, it's basically like you've reflected this diamond off of the, like if that's a ground plane or you're throwing something against a wall, this is like a reflection pretty much. Or it's also, you could also kind of think of it like you folded over half of a origami or something like that. So what's happening here again, just to reiterate, this is the x position of our geometry, and the absolute value is kind of like folding or reflecting it, and then that is getting set or overwriting itself. So we're just saying set the x component or the x direction of the geometry, equal to its folded self, if that makes sense. So hopefully that gets it a little bit more in your head. If you're out of date or anything like that, try to get to my shelf, and here's a new version of the file with all the Vex code and everything like that. All right. So that's the idea here with this absolute value, is we're reflecting it or folding it to be above the ground. So if you want to do something with Vex, like you're eventually filling these lines up to be quite long and you kind of lose track of things. Instead of comments, another thing you can do is create something called variables. These are just temporary labels that hold pieces of information. So I could make something that's a float. Float just means a floating value number. Another thing is an integer. The floating number holds fractional values, so decimals. The integer is just for whole numbers. So for like counting days of the week, you would probably use integers because you're just saying like 5 days from now. For maybe something like time, you might want to use a float. So if you're saying like 1.5 hours from now, you want to do like 1.5 or something like that. This is Vex. It's part of Houdini. Another good reference for everyone is if you just go to Vex language reference from the side effects documentation. This is a bit difficult to read just because it's like a big brick of text, but this is kind of like the underlying way that the language works in terms of comparing it to other languages and performing operations and stuff like that. It's not really intended for like an introductory tutorial. It's more of like a reference or a glossary, because it starts out some very advanced topics and stuff like that. But it's a good reference card or whatever to have. All right. So we're talking about variables as just temporary things that hold information. So I'll do float bounces, and you just put a number into it. So we'll say maybe we want this to bounce 4 times. We'll set it to 4. You can see it doesn't add anything to the spreadsheet. If you want to actually add this as an attribute to the geometry, then you use this @ symbol. But for just temporary bits of information that are getting used internally for this bit of code, it gets thrown away after the code runs. You just use these variables. So I'll just copy this, and instead of multiplying this by 1, I can multiply it by bounces. So if I get rid of this 2, then you can see it's bouncing 1, 2, 3, 4. 4 times. So sponsored McDonald's, the golden arches. Yeah, if you want to make the McDonald's logo, you can set this back to 2 bounces, and you have the golden arches. 99 billion served. So this just makes your code a little bit more readable. It's when another person reads this, or if you come back to it a week from now, what you're seeing will make a little bit more sense. I could kind of expand on this a little bit more, remove this number, and I could make another float and just call it pi and set it equal to that. So then if I multiply this by pi and then the number of bounces, everything is becoming a little bit more readable, or just it's less busy, it's less confusing to look at, if that makes sense. It's like instead of multiplying this by numbers which could have been arbitrarily picked by you, the intention behind what these numbers are doing is a bit more clean or labeled. So I kind of like that. It's kind of like if you're naming these things here, you're kind of describing like what your intention is with that operation, or what you're doing with it, essentially. The variables or these things is more akin to like the constants here. So if I wanted this to be pi, setting it to that and then calling this pi would be the exact same thing. And then again here doing like bounces. This is actually internal to everything, but it's a little bit just it's beyond the scope of this. Yeah, a lot of people do VOPs instead of VEX. I think a strong knowledge of VEX is super useful, especially as you get into more complex things. So this is what we're going to end up making today. If I was to create this in a single VOP, it kind of would end up in a tangle of nodes and stuff like that. So I think knowing VEX is a pretty useful skill to have. So that's the idea behind variables and kind of why you would use them. We don't need this information sticking around on the geometry, so that's why you're doing it like this instead of using the @ symbol that would get actually added to the geometry as an attribute. So this is just temporary kind of storage, and this is permanently stuck to the geometry or part of the geometry. So if we could go no more McDonald's, go to 6 bounces, and our ball or our whatever we're throwing is bouncing trajectory of 6 times. So it's a useful, kind of more human readable way to see what's going on. So the next thing we're going to want to do is have this ball lose some momentum or height over time. So like gravity or other kind of other properties are usually acting upon these. If you throw something, it doesn't bounce as high the next time, depending what material it is, but it always loses a little bit of momentum or springiness. So if we want to model some kind of decay or something like that, I'm just going to go back to my starting line. Just call this maybe the graph. This will be our bouncing. So there's a few different ways to model this decay. But basically, if you do like the y position is equal to 1 minus the y position, then we've flipped it around. So everything is decreasing. We could do this over here. So if I do multiply this by 1 minus the y position, then we've kind of got a ball that loses a bit of momentum or speed or height kind of as it keeps bouncing. I don't think that this is the most physically accurate way for something to decrease in momentum. We might want a little bit more control over that. So instead of setting things up in this way, there's a few other ways that you can represent decay. One of it is doing a more complex mathematical function. You could do 1 divided by the exponent of the height times itself. Whoops. All right, let me see if that works. So if I go in here and change the height overall, you can see as time progresses, it keeps getting closer and closer and closer to 0. These numbers keep getting smaller and smaller. So this is a really nice function that over time will just keep getting closer and closer to 0 until it just is like close enough that the computer just decides it's 0 in terms of like internal representation of the number. So this is saying the exponent of y times itself. So this is doing kind of an exponential decay function. Again, if you just say this is exponential decay, if you want to make this a little bit easier to read, you could replace it and you could set something to the power of y to the second. So you can see the result here didn't change at all. Power of y times 2 is the same thing as just saying multiplying it by itself. So again, this is just something with coding or programming. There's many different ways to do the same thing. The same thing with VOPs, if you're familiar with it, like you could wire stuff up differently. There's different functions to do things. For example, with this, there's a node called the swizzle. If you want to use it, you could use it to set like all of the components to 1. It's the same idea as just wiring things up this way, or setting all of the components to 1 component. It's just a preference of styling and how you want to represent things. So these are 2 different ways to do the exponential decay. If you want to stay up to date, we'll do another publish of the file. If you download that, or if you just have the shelf tool installed or whatever, you can click it and you'll be up to date where I am right now. All right, so the next thing we're gonna do is just apply this. My line got a little bit too long. I'll just go back to how it was here. What I'm gonna do is create another float so things get a little bit more clear. What I'm gonna do at the start here is say, this is our time, and I'll set that equal to the height. So if I start to replace some of this stuff, hopefully things will become a little bit more clear. We'll see how it goes. So just looking at this, if I delete everything to the start, what we're basically doing is saying is, if we don't do this, we haven't changed the geometry at all. I'm just making an internal variable of the height and saying that's also going to represent the time. And then as soon as I set the x position to time, we're moving horizontally as time progresses or as that variable increases. So that's why I've named it that way. If I go over back to our file, things are a little bit more clear now. So instead of keep like reading and writing the height, hopefully this is just a little easier to keep track of what's going on or what you're doing internally. So now if we want to move in our exponential decay function, just going to use this top one, do 1 divided by the exponent of y times y. In this case, it's going to be 1 divided by the exponent of time times time. And then I do need to put parentheses around everything like this. And then you can see we have a little bit better of a bouncing ball that's decaying over time. So the parentheses is, if you're familiar with the saying or whatever, it's another geometry class thing that gets burned into your mind, is the please excuse my dear Aunt Sally. It's just the order of operations, parentheses, exponent, multiplication, what is it? PEM, division, addition, subtraction. So the same thing here with these operations, they get performed in that order. If I don't do the parentheses, looks like I'm okay for this situation. I'm just gonna go back to them to, sometimes it's better just to be clear as to what's going on. Is it kind of like adding comments to your code or stuff like that? So if I increase the length of this line, because I'm setting, just going to go up with a lot more points so that aliasing doesn't happen. Because I'm setting the top thing, the time attribute or the time variable from the height attribute or the y position, as I increase the length or the height of the line, it has the same effect as increasing the overall time of this like bouncing ball equation. Is this hopefully starting to make sense to some people? Following, maybe some light bulbs are going off in people's heads. Starting to make sense, hopefully. So that's a cool thing to do. Let's start to move forward now, and what I'm going to do is just use this add node instead of running over a line. I'm just going to click this here. All this does is create a single point or a single bit of geometry, just one point. There's one position, one coordinate in the middle of the scene, or everything is 0. It's just initializing or creating a single point. Then I can take this bouncing equation, just move it underneath to apply it to this. Nothing happens because the way that we've wired everything up. So it's because we don't have an input height. So we don't have any information being fed into this. So instead of that, I can do a special variable, a special attribute that's this time. That's referring to your global Houdini scene time. So now this kind of virtual attribute, this gets set to, or it represents whatever the timeline or your scene time is set to. Usually I click this real-time toggle. That just makes sure that your playback rate is locked in to be 24 frames a second, or whatever. If you go all the way to the bottom right and do global animation, whatever your frames per second here is set to, it will make sure you aren't playing like too fast or too slow compared to that. So now we have our animation of a kind of bouncing ball or something close to it. You can see it looks a little wacky though. We do have a big issue right now, and that's just that this horizontal movement, or our X position, or the X component, is being set to time. So just linearly, as this scene increases, or you could even see it's kind of synced up. As the play bar happens, the point just moves over, and it's basically set to exactly what the play bar is representing. So if you're familiar with balls or with projectiles or stuff like that, if you throw them or whatever kind of surface it's sliding along, you have friction, and the movement or the rolling of it slows down over time. So we're going to try to mimic that or put that in now. I'm just going to go back to this graph, and I'm going to do a new function. It's similar to this exponential decay, but instead of, whoops. All right. So instead of it looking like this, instead of it set to this, what I'm going to do is set the exponent. I'm going to do parentheses again to define or make sure I'm following a certain order of operations. And then I'm going to add a 1 minus. So that's just inverting our space here. So it's kind of like flipping everything around. So just taking everything like that and flipping it. So anything that's 0 becomes 1, anything that is 0, anything that's 1 becomes 0. Vice versa, it's kind of remapping everything to just invert the range, if that makes sense. And then I can further kind of sculpt this or shape this line using the power function. I'm going to do power right here, and then over here you could start with maybe 2. Uh-oh. Something horrible has happened. So I've messed up my parentheses. This should work. Something. I've done something wrong, I think. Let me restart this. Everything's going wrong. All right, so we're gonna do the exponential. Should not have. Let me try it again. So I'm gonna do, this is 1, divided by exponent power. Then I want to do my power function will be p, the y position, times itself. Okay, I think I realized what I was doing wrong. Okay, now it's working. So this is just, I think I've messed up my order of operations before with the parenthesis in there. So this is just giving us a little bit additional control over things, the shaping of this fall off. So in this case, you can see what one is basically unchanged. Two, kind of just using this as like a contrast or a shaping function. You can go with numbers that are less than 1, like fractional numbers. And then you can see I'm able to get kind of curves with nice slopes to them. So up here, this was our exponential decay for the height of the ball over time. And then what this is going to be is like the speed of the ball over time, or the horizontal movement. So at the start, it's very quickly moving over, and then it will slowly approach or roll to a stop over time. So this is a little bit of a wacky function. This is no longer what's considered exponential decay. I've just gone in and kind of like customized it a little bit. If you're familiar with doing a lot of animation using coding languages or procedural functions or stuff like that, I have a resources page on my website. And I think if we just take a look at that quickly, you look at tools, math for motion. So this is a really cool visualization of kind of a lot of some of these functions that I've gone over. And just as you use more code or kind of little equations like that, you might come up with your own that you find useful and store them away or reuse them or whatever. So that's the idea with this one here. So it's just kind of a modification of existing functions or ways to put them together or whatever for what you need to do. So this link is right there if you want to go to it. That's a really good way to visualize it. You could kind of do the same thing in Houdini, make your own little visualizations or animations or whatever like that. So we look at the original bouncing ball that we had, and we just want to add our kind of like motion, or I'll just call this is like a fake friction. Finally, math is useful. Yeah, I think it's something that you see quite a bit with, when you use it more, you'll recognize it. If you look at like a bird, how it's flapping its wings, that motion is very similar to a sine wave, the wing motion going like that over time. We're kind of modifying that and using it to show like a bouncing ball, like doing folding and different operations like that. So it's just something, I think, as you bash your head against it or run through it, it might take a couple of times to get it clicking with your head. Squirrel hopping, jellyfish going through the water, like everything could be represented with sine waves of locomotion, motion, and just all kinds of things like that. Wheel spinning, circles, tons of stuff. So what we want to do now is just fix our thing. We want to add in this friction equation. Or just motion decay, whatever you want to think of this. This was like height decay. DC? decay. All right. Again, if you want to get caught up to where I am right now, here's another link in progress or whatever to my scene. So hopefully as well, you can start to see we're getting close. Halfway there maybe. We'll end up here kind of in the next 30 minutes or something like that. But yeah, this is the idea, just breaking it down. So here's our bouncing, single ball bouncing. Again, you could see over here it's starting to get there. All right. So we want to add in that decay function. What we can do is put it in instead of just time. We want to do 1 minus 1 divided by. Let me just make sure. All right. The exponent, power, time, multiplied by itself. That's just like a exponential increase now instead of just linear. And then this is kind of just the shaping amount and should be good. That's starting to make sense. Starting to look a little bit more real. This is our decay, our friction amount or whatever. We could do another float at top, and this would be the distance. This is going to be the total distance that we're traveling. If we just set it to 1, this is basically unchanged. But this is like the total distance that the ball would be traveling. I think we could just do it in another line. One thing you can do, like if I want to do here, set the p dot x times distance. Right now, it's still just going from 0 units to 1 unit. If I want, saying we're rolling this ball 10 units, then you can see that going from 0 to 10. Another shortcut that you can do, instead of having this equals this times, this is equal to itself times the distance. If you shorten this function down and you do multiply equals, this is doing the exact same thing. It is kind of a shorthand. Instead of just equals, you're saying multiply this by itself and set it equal to the result. So going back to this and then going forward to that is the exact same thing. One more thing we could add in might be the height. And right now it's kind of equal to 1. This we're going to put in after y. So I can do the same thing here, the y position, and scale it by the height. So again, this is unchanged, but if I set this to 15, got to zoom out, but then this is like your ball is bouncing very high. Starting with the first bounce is going to be 15 units high. You could go again with a decimal, and then that's like a little hop. So just different ways to keep track of what's going on. Yeah, I can change the display size. I think if I do a disk, It doesn't work. It's cursed. All right, let's just go back to this. Set it like that. Is that big? Let's see if this... Boom. Look at that. All right. So this is going to be the start of our bouncing equation. Again, if you're keeping up or following along, are you joining in the middle? I'll do another session share, so you get up to date if you want. So now we're going to go from this to making a ton of balls. So the really useful thing about Vex is that it automatically runs simultaneously over the geometry that you're working on. So all of the points or all of the geometry elements are processed in parallel. You don't have to do anything with your code to update it to go over more geometry. So if I just do a point generate, this will give you, instead of, if I just do 1 point, it's the exact same thing that I was doing with this add SOP of just creating a single point, but this has the ability you can make as many points as you want. You could as well do like a copy and transform and just make more copies of this original point. Doing the two of these is you're basically recreating it, or this is a simpler version of doing these two nodes at once. All right. So now we're bouncing or rolling a bunch of balls, 329, but they're all stacked up, so you can't really tell them apart, or there's no way to differentiate them. They're just all in the same position, or they're all overlapping. If you turn on the point numbers or whatever, you could see, just try to make that marker size bigger. Whoops, might be the font. All right, so you can see all of the point numbers here are overlapped or just stacked up on each other. The next way, or the one thing you can do to split that up, you could offset the time for each individual point. There's no way to do that very easily without knowing some information about the points or the geometry. So if you take the PTNUM, this is another somewhat special variable or attribute that is the point number, or what's happening over here in this column. So it's just the index number of the points, or each geometry number. And then I think I want to switch this over maybe to subtracting it. Or I think you could do it maybe plus. And then you could do maybe time minus, I don't know, 32. So we're changing the way that these balls bounce, offsetting them over time by their point number. Thank you for the Amazon Prime, Jesserif. Let's go. Thanks everyone for subscribing, rating, following during this demo, this stream. Much appreciate any of the community support behind it. What I'm going to do is try to make this point number offset a little bit more easy to understand. So we'll take, right now we just go back to where we were. So everything is starting at 0 and then going to 1 in sync. Let me do time minus, we'll do the point number, but we'll divide it by some bigger number, like 512 or something. So that becomes a little bit maybe easier to understand. One of the issues here is that we're getting some negative numbers. At the very start, time is 0. And then as we subtract higher point numbers from it, we're having like negative time values that's causing a little bit of problems for all of the code we're doing. There's different ways to fix this or to handle it. You could do a clamp function to make sure your numbers don't go below 0. If I do time equals clamp time, then the minimum and maximum, like that, then we don't have that issue with it at the start. You can see the end is a little messed up because I've clamped the highest value of time to 1. If I go up to 32, we don't have that problem. You could make this a really big number if you wanted to, but you still see these points at the start. So that's one way to handle it. Another way to handle it, or another really useful part of thing you can do with Vex, is using functions that will remove or add geometry to itself. So we're going to do a conditional statement to take care of that. We could do it at the very end if we wanted to. That's just like an if statement, like that. It's basically doing the same thing that the group parameter does with Houdini. You're basically saying if this condition or if this statement about the points or the geometry is true, then run the following code over it. So in this case, what I could say is if the time is less than 0, if we have negative time values, then we'll do the following function, and we'll do remove point. And you'd see all these things that highlight or turn out turquoise. These are all just something that's called functions with programming. It's the same thing when we were looking at VOPs earlier. Those are all the equivalent of nodes. And then what you put inside of the parentheses of it is like you've wired it through the input of the node, if that makes sense. So with the remove point, when I was finished typing it, you can see it gets the little tooltip. You could also go online where I was saying the Vex language. Did I link that? There's also another thing here that's just functions. Reference down here, functions. And then this is a list of all the functions that you have available to you. So it's kind of like a glossary. It's super long, it's somewhat intimidating. But if you're searching for a specific one, they have pretty good, it's very instruction manual, very technical, but it's just the documentation of what this function is doing. So add point will add a point to the geometry. Then we also have remove point that will delete a point from the geometry. So in this case, we want to remove the point if the time is less than 0, if we have negative time values. We're going to do 0 is just removing the point from itself or the current processing geometry. And the point that we want to remove is the current point number. So now instead of this, you can see we start with just 1 point, and then we have more points over time. So if I divide this, or get rid of this division, what this should be doing is every second rolling or throwing another point. And it kind of has the illusion of, search the term Vex fun. So this over time has the illusion that we're creating or throwing a point. But what we're basically doing is saying if the time for the current point hasn't started yet, or if it's a negative value, a negative time value, just hide it or delete the point or the geometry. So hopefully that is making sense. What you've seen here is what we were able to do is offset the code that we're running or make kind of unique outputs based off of the point number. You can extend that even further if you use the random function. So instead of just giving you the point number, what this will do is generate a random number between 0 and 1 based off of the point number. So what it's done over here is just spread out the points and offset the starting time by a random number between 0 and 1, or 1 second. If I wanted to spread that out more, I could multiply it by 10. So what this does is says, make the start time offset it or scrub it back, start between a random time between 0 and 10 seconds. It might be, let me just start with like 10 points. That should be a little bit more clear. So just 10 seconds is the duration of the scene with 240 frames, 24 frames a second is 10 seconds. So we're just saying start bouncing these balls over the duration of the scene with where we are right now, pretty much. Hopefully it's still making sense to some people. Sorry, I was moving a little bit fast for people just starting out. We're just going through this more and more, and things hopefully will start to click for you. So if we wanted to, we could keep doing this random function in more places. Could change the distance we're traveling and modulate that or multiply that by a random number. We get this error here. You could see I've made a mistake, a coding mistake. If you're starting out, you probably get this all the time. It's frustrating or whatever, and sometimes this error doesn't make sense. They've improved this code editor a little bit, so you can see I've got like my Microsoft Word, I've got a spelling error, or I've got a syntax error. This little red thing will indicate what line you're on, and then this is saying what the issue is. If you do take the time to look into this, you can see it says unexpected semicolon. It was expecting a parenthesis, and then this is the line and the character number. So line 3, the end of the line, or character number 44, it was expecting a closed parenthesis, but instead it's seeing a semicolon. We just close that and we've got it fixed. So now this distance, we're only going to throw the balls or roll them a random distance between 1 and 10, or 0 and 10. So instead of throwing them all, you can do it like that. Instead of throwing them all 10 units, we're just saying override that or scale that distance of 10 by a random value for each point. Pretty cool. And the same thing for height, can do that as well. Some of them get 0. You can see right now we're kind of synced up where the one that bounced a height of 0 also traveled a distance of 0. Sometimes you might want to make that unique for the points. So like something could not move very far, but it could still be bouncing pretty high. The way that people do that is they'll offset these point numbers before they generate the random number. So this is called a seed. Right now this is all using the same seed, or it's using the same kind of key to generate your random number. If you make them unique generators, then you'll get unique results from it. So people will just offset or add a random number to it. So if I do that, then you can see some of the ones that are going a distance of 0 might still be bouncing. But before, when they're all using the same seed or they're all using the same generator, you'll just get weird, you might get some weird or unintended results or artifacts of that. Things that are rolling a distance of 0, like sometimes you want them to be unconnected or unsynchronized. So for example, with the starting time, if I want that to be unique or untied to the distance, we'll just get a different new random number. It's kind of like rolling a dice to generate this number. If you roll one dice and use it for all these outcomes, that's like not adding or changing it. When you're adding a number to it here, this is like changing to a new dice or rolling another dice. You're just generating another random outcome. You guys are starting to see how we're going to get here? That's how the seed works. If you were wondering all this time, all these years, that's how it works. I think the most intuitive way to think about it is like you're using another dice. If you're switching to rolling another dice, if you leave these as all the same number, you're basically going to get the same result for each one, or you're rolling the same dice. It doesn't have to be necessarily. People usually just type in random numbers because they're lazy or they just are in a hurry. If I do it like this, you could think of it as like the actual dice number. We're using -1 here, -2, -3, and it will just generate another random number. It's the same idea here if you've ever used the attribute randomize. That's why they actually use an image of a dice, because it's of that concept. And then options here is global seed, and you can change that as just a random number. So they're doing something here where every time you make this node, that seed will get set to a random number. It's the same idea because you don't want to keep generating random numbers using the same seed. All right. So we're getting stuff that's pretty interesting, but we don't have any, you could see over here what I did. Things can bounce off of walls, and they're also starting in different directions. So it's a little bit more, there's still a few more steps we need to do to get there. We're not 100% of the way there. So anyone has any ideas to get things going the other way, or bouncing off the walls? All right. So we want to do that. We can do the same idea that we were doing here as this folding. People that remember, you could do it with that another if statement. Was you 100% on the right track, Jabram? So another way, if you wanted to like recreate the absolute value function, if I did instead of this, I could say if the x coordinate is less than 0, multiply the x by -1 or flip it around, and we have the same result. You're 100% on the right track with that. I usually like to stick with these absolute value functions just because it's a little bit, I don't know if it's optimized in terms of performance, but it's a little bit more pure in terms of readability, or I don't know, maybe you're used to seeing things like this. In terms of just keeping things on one line and stuff like that, it's a little bit simpler. So yeah, like I was saying, for folding, and then up here, if you're picturing the balls, they're rolling, they're kind of reflecting or colliding against that plane and going down below and then fold it over or bounce back to the other side. So you could do, if you want to keep doing or change the position that you're folding things. For example, everything right now is folding at the origin. If I wanted to fold at -1, I think I can just do offset that. Unfortunately, that shifts everything over by 1 unit. You can just fix that at the end by subtracting the same number. So it's kind of like the pivot of a transform node or something like that. Moving the pivot around, we're folding everything, but we're using a pivot or an origin of -1 for this. You can go do an additional fold if you want, or fold the other way. So if I do p dot x negative absolute value, and then I'm going to set that for the negative x coordinate. And then this fold, maybe I want to do it at 5 units. So we'll just do +5 and +5. So then I've done 1 fold here and 1 fold like that. Again, you kind of think of these like bounces, boom, and then it bounces the other way, like that. If you wanted to practice with this kind of stuff some more, sometimes going back to just the single line, doing a graph like this can be helpful as well. So just to kind of refresh or go over that again, what we've done, just for this line, I usually make a time, set it to the height, the y position. So then we get this horizontal, the 45 degree, this linear corner. And you can do is set this so over time things move over. Without it, just have something going straight up. So over the height or over time, we'll also slide the line over. If I did maybe, let's do the height, the y position, negative time, then it's going straight down. If I did 1 minus time, then we're doing basically the same thing as the y equals mx plus b, the slope line intercept. Our intersection is going to be 1, and then the slope, we haven't multiplied it or changed it, so it's still linear. We did flip it around because we did a negative number. So I'm showing this because if we want to keep going with the absolute value, we'll just do equals absolute value like this. So this is our fold or our reflection across the ground. And then, like I was doing over here with multiple folds, if we want to fold it again up here, when it's like bouncing again off of something, you can do it with a negative and then another negative here. Kind of have to like invert it, do the operation, and then invert it again once you get the result. And then I think we want to do maybe 2 units. And looks like I did it. I have an issue here where I didn't specify the y position, so it was just taking the wrong component of the geometry. hopefully this is helpful. If you go back, experiment with a line. It's a good way to get a handle over these functions. Just for me personally, I was spending a long time practicing it, trying out different ones, seeing what the result gets. The idea with doing it on a single line is instead of doing stuff in 3D space, things will get can get a little bit confusing or complicated. So if you just go into something that's like a 2-dimensional plane, or you could even go into a 1-dimensional plane, 1-dimensional space, these operations get a little bit easier to visualize or hopefully start to make a little bit more sense. All right. So go back here and see where we are with the balls. If you want to get an update, do another version of the file, you can start to play around with these different folding ideas, reflection ideas, and all that stuff. All right. So down here, we did our first reflection. If I get rid of that, then you can see we no longer have like bouncing balls, but maybe they're in a water or something like that. They're like bobbing up and down. So that was the idea behind this first reflection. Now they're bouncing off of the ground. So again, to do another fold or reflection, we can just do an absolute value of the x or the horizontal component. So we'll set the x absolute value to itself. Whoops. To itself. So it doesn't have any effect. We're basically taking anything that would be on this side of the x-axis and flipping it over to this side. But it doesn't have any effect because we don't have any balls that went on this side. So what we want to do is, if we go back over here, like where we were folding across from this, you do a negative to flip everything around, and then another negative to revert back into your regular coordinate space. That's how you fold the other direction. You don't need to do it when you're folding this direction, but to fold going the other way, you need to do this kind of double negative. So we'll do, set that up right here. And what we've basically done is just flipped everything around to the other side of the axis. We can add the offset now. We'll do 5 units. You just need to add it in both places. This is kind of like a pivot or something like that. So now, anytime the spheres travel longer than 5 units, our overall distance is always going 10, and then we've modulated it by a random amount. So not too many of them are going to bounce off of that wall. If I did my distance, which may be 30, then you can see more of them are bouncing off of that wall. This is pretty cool. We can do our other bounce, just copy and paste this to kind of reuse it. Then I'm going to take this negatives out, and instead of starting or folding, bouncing off of +5, I want to bounce off of -5 units. So just flip these operations around to negative numbers. You can start to see what's happening. So you can see we have an issue now that things are escaping. They're not bouncing off of the other side. This is because we're basically doing this first fold once, and then we're folding this way. And then we're basically running out of times that we've reflected things. So if you wanted to keep making sure that that's happening, you could just keep kind of repeating these operations like this. And then you can see it is following those bounces. if I make my distance really long, eventually you can see we're still, basically this will only let us bounce 3 times until it runs out of reflections or bounces. So instead of just going in here and doing this a bunch of times, you could do that, but it's, again, like we've been trying to up here, stay very clear and readable. This is a bit of a mess. So instead of doing things this way, we can use really important coding construct or syntax that's looping. So you just tell it to keep repeating this operation several times over and over again. So if I just do for, the way that you set this up is you have a loop iteration. Usually people would call it I. You start it at a certain number, so you set it equal to 0. We're starting at 0. Then you have a condition for how many times you want this loop or this code inside of here to be executed. So we'll say, well, I is less than your condition. It's maybe 700. And then your increment. Usually people do I plus plus. So plus plus means increment it by 1, add 1 to itself. This is the idea behind C++ is like a in-joke or whatever. They added that syntax capability with C++, I think, and that's why they went from C to C++ or whatever, because they expanded more capabilities with the language. With Vex, it's built off of C++ and all those kind of the same building blocks or the same ideas behind all of those things. So that's why some of the syntax looks the same, or reading it will look the same to people that have used those programming languages. And then for multiple lines of code below it, here I didn't need these brackets, but if you're going to be doing more than one line, then you need to use these brackets. It will tell it basically when you're starting and ending your loop. And then people, for readability, will just start to indent things or tab them over. In this case, it doesn't, I don't think it matters. Like the compiler will ignore, doesn't pay attention to it. But for readability, people will usually indent things over or tab it over. And then when you're looking down, you can basically assume anything that's shifted over one block is being part of this condition or the loop. And then there's one thing I forgot to do and just tell it that this was an integer type that I wanted my iteration to be. So I is the iteration number. All right. So now we have our loop. It's basically, this is my shortcut, or this is a simple way instead of copying and pasting this line of code 700 times. This syntax editor would get really long. It would be a horror to edit and just a mess to read and everything like that. So that's what internally the computer does, is basically say, we're just going to keep repeating or copying and pasting this operation 700 times. If you want to test it out, I could say just, well, it's 1. And then you can see my bouncing or my folding of the space is only happening 1 time. If I set it to 12, then these guys will be able to bounce off of 10 walls before they escape. If I made my distance a really big number, maybe 600, you see some bounce more than 12 times and they escape. I could just keep making this a really big number if I wanted to. Sometimes when people just have it, they've just set it to a really big number to say basically infinity or never stop running this. You have to stop doing it at some point or the computer will just get caught in an infinite loop. But the really high number is saying like approximately keep doing it enough times. You do 666 if you're a satanic devil worshiper. You could just set it to 100,000, or sometimes people will do something like that. These operations are pretty inexpensive, so I don't have to worry too much about slowing down my code too much, but if you're doing a ton of expensive functions or operations inside of here, then you might be more worried about running out of things. And you could do an optimization and say, maybe find out a maximum distance and then set your limit of bounces equal to that, if that makes sense. So we're nearly there. We're pretty close. We just have a few issues now, is everything is starting at the middle, which is a little weird. All of our balls that are bouncing, they're all starting at the same height, or they're starting kind of at the same arc of the curve, which doesn't make a ton of sense. And then we just have some artistic parameters or stuff we might need to tweak, maybe the total distance and the total height, if we want some to start higher than others and stuff like that. Got some magicians, Siegel Rush, in the chat. So what we want to do is, if we want to change our starting position, if we want to change our starting position, I think we can do that if we just say at p.x equals, I don't know if I want to do that up there, because I've already, then I'm overwriting it, or I'm setting it to a new number down here. So it would essentially be ignored. One thing I can do down here is just offset it or add a number to it. So I'll take the x position and then just do a plus equals, or say add a number to itself, and that we'll just say is another random number. So let's do a random number based off of the current point. This is going to make it unique for everything. I could keep my counter like this, 1, 2, 3, 4. And let me get rid of some of this. It's just getting a little bit out of hand. I might want to add or make that number a little bit bigger. So you can see now some of them are starting to roll. They're not starting to get thrown from the middle of the screen or 0. They're starting slightly offset. So with this, we're basically saying offset the starting point by a random position between 0 and 5. That's pretty cool. One thing we could do is just going to trying to think what the best way is to do this without getting too following too. I think I've already gotten pretty complex for most people, but we'll just keep going. So let's say do a float is offset. So this is going to be the starting position, offsetting the horizontal position. Could call this horizontal offset, and set it to 5. And then if I do my position plus equals, whoops, all right, my x position, offset or add the offset to it, plus equals horizontal offset. Everything is starting 5 units from the origin, or 5 units to the right. And then it's immediately being reflected, or because we've set up this loop. One way you could do multiple comment blocks is this /**/*. So if you want to ignore an entire chunk of code, this will tell it to start ignoring it, and then doing it the other way tells it to stop ignoring things. So if I just want to turn off temporarily or have it ignore my folding, just say this is my reflection, horizontal edges. So just to describe it a little bit better. And then if I want to ignore that whole process, you can do that multi-line comment or multi-long ignore. So by shifting everything over here by 5 units, we're basically starting all of the points over here. If I want to start some at the other side, one thing I could do is say if we'll generate another random number. This will be random based off of the point number. We'll just say -4. This would be another random number unique from these earlier random numbers we generated. So if our random number is less than 0.5, if you remember, these random numbers that get generated are always between 0 and 1. So if you compare it and say if it's less than half or less than 0.5, you're saying basically 50% or half of the points this will happen to. And I'll say we're going to take horizontal offset and multiply it by itself times -1, or flip it around. So this 5 becomes -5, 50% of the time, or for half the points. So let's say this is half of the points, 50% chance. So now, randomly, if we want to do another random animation or random probability, can do it like that. And then, depending on the point number, half of the points will start on going in one direction or from one side of the box, and half of the points will start at the other side of the box. This will say, move the starting position horizontally. So especially as you're starting out wrangling or programming, writing VEX code, as you make bigger wrangles, or if you just want to remember what you were doing, it's really useful to add these comments or notes or whatever you want to call it. You'd see with this thing that I just was typing up an hour ago or something like that, instead of having the comments, if I just look at this math function, I might have forgotten, especially if I didn't name the node, I might have really forgotten what this is doing. Especially if you're doing multi-line complex things, it becomes really, really useful to do that. I'm just going to get rid of some of this extra space. All right. You can as well add some comments over here. It just depends up to you, your coding style. So for this one, maybe I'll just say delete points with negative time value. So depends, it's up to you. Like with this one here, if I wanted to put that there, I could put it there. Just be careful, like if I try to insert it, then you can see it includes that bracket. So it's just whatever, there's certain standards, but there's enough schools of thought now that kind of everyone is slightly doing their own thing, but whatever you decide is the cleanest thing that makes the most sense to you, I say just stick with it. Because this essentially what these notes are for is readability for yourself. As you start to work with like other artists, other Houdini people, you might want to agree on a standard with your team or something like that. You start to share wrangle nodes and stuff like that. It gets easy. People are using different styles and stuff like that. So it's, if you're working on your own, it's up to you, especially learning whatever helps you learn or keep track of things the best. But people will stick to different standards for different reasons. Then if you're in a hurry, the client or the producer is coming over in 10 minutes, then you just don't make any comments and you just have things that are named very poorly, and you come back to the file a week later and you close your eyes and you just go to the bar because you don't want to deal with it. So we're getting pretty close now to this final animation. Just go in, and now that we've named everything pretty clearly, I'm going to go reduce my point size a little bit. Comments are easier when other people see your code. Yeah, for other people to see your code, and then especially for yourself, as more time goes by, the more you'll appreciate the comments you've written and everything like that. As you're writing it, it doesn't make a lot of sense to you because you're like, I know why I'm doing this. I don't need to make a note to myself why it's happening. But you'll appreciate them, like you could see even clicking on this stuff earlier. This is just a basic sign function, so it's pretty self-explanatory. But having here, it's really useful to kind of break it down into descriptors or stuff like that. The future you is a separate person. All right. So if we want to get closer to that final output, looks like here my distances aren't super far, so I might want maybe 30 to be my maximum distance that things travel. I might want like 15 to be the maximum height. Another thing that I was doing for that final result was starting to use the exponential functions. So for shaping this randomness here, or the probability of it, if you use a power, we'll say the power of 2. This is kind of like a gamma. So it's saying the majority of these bounces won't be super high, but you'll get 1 or 2 outliers that are bouncing higher. Again, with these shaping functions, if I go up here and just get rid of this stuff and just look at it this way. So when you generate random numbers, this is kind of what's happening, is it's giving you a linear distribution between 0 and 1. The likelihood that something becomes 0.9 is just the same as the likelihood that something becomes 0.1. If you do a power of 2, what that's doing is changing the likelihood so that the results are more exponential. I should get rid of this length because the random number generator is only giving you results between 0 and 1. So this is a little bit more clear. So now what's happening is like the majority of the points or the majority of the outcomes are very small numbers. And the likelihood that something is a higher number is very slim, or there's not that many points. If you want to do things the other way, if you use decimals, then you're bending or shaping this line the other direction. So go from like this, and then the majority or almost all of the values are 1 or close to 1. You seem to be into a deep of a question. Let me finish up this lecture. I'm trying to record, get it into a solid block of like this task. All right. So we're back here. And we're just going to shape some more of these bounces. No worries. I'm gonna take the exponential here, and if we do like an exponent of 12, then you can see very little points will get a very big height value or a maximum value that they'll bounce at. The nice thing about, again, with this code is that it runs simultaneously or parallel over all the geometry. So if I just add a bunch of points, you can see very quickly we can control the number of bouncing balls that we're making. So it's a pretty cool way to visualize stuff or change the outcome, change what you're simulating pretty quickly. It's kind of like a fake simulation. It's all using code, so it's not like time dependent like most simulations are in Houdini. This is just a good way you do like user control. The next thing we're going to do is offset some of these in Z. So if we look at our example here, with this grid, you can see some of them are further forward than others. So they're offset in depth. We can do that pretty easily, very easily, hopefully. If you just do we haven't modified Z at all, so it's always just been 0, or it's been like a flat two-dimensional result the whole time. So we'll say the Z coordinate or the Z position is equal, or set it to a random number. Again, we're going to want to use the point number. And it looks like we've used a few things here. This is sometimes why people will just type in a random, semi-random string of numbers. What we've done now is set it, slid things forwards and backwards in space by a random amount. So if I want this to be 5 units, then we start to have a little bit more depth. I'm going to just get it a little less crazy. All right. So basically all these balls now will be going between 0 and 5 units in depth. If we want it to be a bigger range or a bigger box, you could do more of it. So it's pretty cool. Let's do, I feel like we're nearly there. Trying to think, maybe for this distance, we'll do a power or exponent. But this one I'll do a number that's less than 1 or a fractional value, like 0.65. So what this is going to do is say the majority of the distances will be higher than 0 or closer to 30 than they are to 0. So we change that, and very few of them now will just be like slowly rolling. So I think it makes it a little bit more interesting. Like the ones that don't roll a very big distance are somewhat boring. This is, you start to do kind of like art directing with these values to shape the overall outcome or the overall results you would get from those balls. Yeah, floating the powers. It's kind of like a gamma operation. It's a little bit like an invert, but basically, if you're familiar with image manipulation, if you do a gamma, I think it's like 0.54 or something like that. Then a power of 0.54 is the same thing as like a gamma of 2.2, where it's like linear to sRGB space or whatever. So it's an inverse relationship or whatever, but it's kind of the same thing as like gammaing is increasing contrast. If you do a power of less than that, it's kind of like decreasing the contrast, if that makes sense. So pretty close to being finished. Might want to play around with maybe more of these points if you want it to be more exciting. We want to play around with this start time. Could maybe just switch this to 2. So now all of the balls will start between 1 and 2 seconds. Looks like I have a little bit too many now. Like maybe just do like 56. I might do 1 to 4 seconds. Then you can see we're getting closer to my end result over here. Basically, I'd set this one up so by the end of it, things start to roll to a stop. So what we're doing over here, we pretty much have the same kind of idea. But yeah, it's pretty controllable. So again, setting things up with Vex this way, you have a little bit more control. Like if you were running a particle simulation, you would see the blue bar at the bottom of your screen, and you would have to keep like resimulating or keep the cache from going. One advantage of using code or working 100% procedurally is that you can tweak things. So I can leave my timeline at the very bottom here, and like distance, if I make that bigger, you're already seeing the result, and you can scrub, and you don't have to wait for another simulation to run. Everything is run kind of on the fly. So there's no caching, no previous results being used or anything like that. Each frame is being computed like independently of all the other ones. So this is like overall, it's a bit of just like a demo, or it's for fun. It's not, there's not a ton of situations where you would want to use this in production or to create a final effect. The reason is because you couldn't do things like other collisions that easily. If I make this sphere in the middle, like if you're using solvers with Houdini, you could add this in as a collider and things would bounce off of it pretty easily. To make this with equations, it becomes a lot more difficult. So that's the reason people eventually split off and started doing solvers and simulations and stuff like that. If you look at like Toy Story 1 or something like that, a lot of effects might have been created this way before computers were that powerful. You can do a lot of other, this is just like bouncing balls. If we get rid of a distance or just set that to 0, then we just have basically things that are falling in place. You could see, I don't know how much modification I want to do. Just going to set my horizontal offset to a random number. Grum Cow, thank you for the tier 1. So now we've just started ours. Things falling in random places. Just going to multiply that to be a bigger number. Change that. And then instead of doing a reflection across the y-axis, I think this one here, I was kind of showing what a reflection was doing, or absolute value. This is why I was making the line earlier before. So here it runs out of reflections. We ran into that problem earlier, and that's why it keeps extending. So instead of bouncing or reflecting off of the origin, another thing you can do is a minimum function. I think in this case I want to use maximum. So this will take 2 numbers, or two arguments, and it will basically give you the higher or the maximum of these 2. So without it, you would have negative numbers. We'll just do here. Everything goes below the ground or below 0. So this is a simple way to kind of keep things above the ground or the origin, or if you have this higher number or a lower number, you can do things like that. So with this bouncing one over here, if we want to change it so things don't bounce, instead they just stop once they get below y, I can do a maximum, and the higher number, whatever is higher of zero, or the current y position. I think, so instead of doing sine here, I would just want to subtract the time from height. Let's do, or 1 minus height. I'm sorry, 1 minus time. All right. So now we kind of have like snowflakes falling. So just doing some variations here to give you an idea, like super prehistoric days, people would go to town programming things. It would be less expensive than writing a whole solver that would take forces into account and keep track of a lot more information. So back in the day, this is how people would approach just kind of the groundwork to computer graphics or things like that for other effects of snowing, falling confetti, sparks, a shower, just all those effects, rain, all that kind of stuff can be done like this. And then it still gets used to this day for game engines and stuff like that. You could imagine if you're playing a video game, instead of running a rain simulation all the time, encompassing the entire world, if you just run some code like this in the shader or somewhere that's inexpensive to run, you'll have a lot. The other areas of your game will be more optimized, or be able to you'll be able to have fancier graphics for other portions of the game. Yeah, so it's going to wrap up for this one. Let me just take my stuff that I was doing over here. I think I can just take these collections of nodes. I'm just going to paste it down here and just color this maybe like a color so it highlights or stands out a little bit. Plug it in. Let me see if I did everything else right. We have some that are too high above the box. So I think just in my bouncing here, my total height, we just make this a smaller number, maybe 5 or something like that. We get something close to it. If I do my camera, I'm just going to copy it from here and go up to my object level, paste it, put it in. Then we have our fun little demo, week 1, pure Vex. Vex introduction for artists, how you would use it to make fun, interesting things. Sorry if it was too fast or too complex for people. If you're watching the VOD, I recommend just kind of rewinding or breaking this down into just watching it maybe in 10 or 20 minute chunks and kind of repeating that portion of it and just practicing things and getting up to speed that way. Yeah, so everyone in the chat, thanks for following along. I'll do one more file sync if you guys want the proper fancy demo version of it. A pretty cool thing. Yeah, and then with my post, the only thing I did special here to get motion blur and that kind of stuff was just if you run the flipbook under effects, motion blur enable. If you just do a ton of frames like that, then you'll get this fancy kind of like subframe motion blur. And again, because we're using math sine functions and equations, you get really nice, beautiful kind of multi-segment or curved motion blur. You don't have to worry about increasing substeps or anything like that. So it's another cool kind of byproduct of running these kind of parametric simulations or animations. All right.